We've seen that the region, the wedge between theta equals 0 and theta equals pi of radius 3 can be modeled in terms of x and y or in terms of r and theta. If we're trying to integrate a function, which again we might consider to be an altitude function or a density function, so that the interpretation of our integral might be a mass or a volume. The mass of a plane region, the mass of a flat wedge, or the volume of a region of three-dimensional space. We calculate the integral of f of xy over this region by first partitioning our polar coordinate description, our limits on theta and r, as we've seen here, and considering just what that partition means, considering a typical interval, an ij interval of the partition, and the contribution of our function and this area to the total integral of the function over the region. We obtained a summation of contributions, which we sort of waved our hands at and took a limit of, and we obtained this integral, which we're now going to interpret and calculate. Now, before we interpret or calculate this integral, let's estimate it. Now remember, we're evaluating the function f of r theta equals 1 over 1 plus r over a region which is a wedge of circle of radius 3. So we're going from 0 to 3 here, from 0 to 3 here, and f of r theta equals 1 over 1 plus r. What are our values of 1 over 1 plus r over this region? Of course, we can't calculate them all, but let's get some indication. If r equals 0, 1 over 1 plus r is just 1. So our function f takes value 1 at this point. For every other point of our region, r is bigger than 1, so that f of r theta will take values that are less than 1, so that by the time we get out to r equals 3, which occurs along this boundary, along this arc of a circle, we have f is 1 over 4. 1 over 1 plus 3 is 4 on the arc of the circle, on the arc of our bounding circle. We could also look at the circles of radius 1 and 2. So that on the circle of radius 1, we have 1 over 1 plus 1, f equals 2, f equals 3 along this circle. And I said that and wrote it wrong. F is 1 over 2 and 1 over 3, so that our values of f decrease from 1 to 1/4 through the values 1/2 and 1/3 as we move from here to here. If we graph our f of r versus r, we have value 1 here, value 1/3 out here, value 1/2, value 1/3 here, 1/4 here. Our function won't be linear, it'll actually have some curvature. We are, however, integrating the function with respect to area, and there's more area out here where the value is 1/4 than there is here where the value is 1/3, or here where the value is 1/2. Our average value of f of r with respect to r is a little less than the average of the values here and here. Remember, those values are 1 and 1/4. The average of those values would be 5/8, so that average of f of r versus r is maybe 1/2 question mark, where this is 1, so that 1/2 is not an unreasonable average. If f of r over this region actually had a value, an average value of 1/2, then what would the integral be? Well, the average value, if the average value was 1/2, and it's going to be lower than that because, again, the lower values cover greater areas, but if the average value was 1/2, then since the area of this region is 1/4 of the area of a circle of radius 3, circle of radius 3, of course, has area 9 pi, and you should be able to figure that out very simply. An average value of 1/2 for an area of 9 pi over 4 would imply an integral equal to about 1/2 of 9 pi over 4, 9 pi over 8. 9 over 8 is a little more than 1, pi is a little more than 3. Just going to say that integral might be approximately 3. This estimate would be a little greater than 3. However, again, since the smaller values of f cover more area, we would expect even this to be an overestimate. So we would expect maybe the actual integral to be somewhere maybe between 2 and 3. So we'd probably expect an actual integral less than 3. We could make more sophisticated estimates. We could figure out the area of this sector, which is just, what, 1/4 of pi, and an average value between 1 and 1/2, probably a little less than 3/4. We could estimate the value over this ring, where the average value would certainly be between 1/2 and 1/3, and the value over this ring. Calculate the area of each ring, add up the average values times the areas to get a better estimate than the 3 that we estimate here. We could also do some slightly more sophisticated things and graph f of r versus area rather than versus r, but we're not going to go into those estimation techniques, and we're not going to require those insights to just do a simple estimate. And the purpose of an estimate is so that we can compare our final result with our estimate and make sure it makes sense.